Welcome to G Fun Facts Online. Today, we're journeying to the colossal king of our solar system, Jupiter. At its poles, a light show rages on, far grander and more powerful than Earth's auroras. But within these shimmering curtains of light are a series of strange glowing spots, marching in a mysterious procession. These are not random flickers in the gas giant's atmosphere. They are the auroral footprints of Jupiter's largest moons, a celestial phenomenon that reveals an intricate dance of immense power. This isn't just a story about pretty lights. It's a story of electrical currents bigger than our planet, magnetic fields that defy imagination, and the surprising power of moons we thought were just passive companions. These footprints are a natural laboratory, giving us clues about plasma physics, magnetic fields, and even the potential for life on these distant worlds. So let's dive into the story of the Galilean satellites, Io, Europa, Ganymede, and Callisto, and the marks they leave on their planetary parent. To understand how a moon can leave a footprint of light, we first need to understand the environment around Jupiter. The planet is wrapped in a gigantic magnetic bubble called a magnetosphere. This isn't like Earth's magnetosphere. It's a monster, generated by Jupiter's rapid spin. A day there is less than 10 hours, and its core of metallic hydrogen. The magnetic field is about 20,000 times stronger than our own. This colossal magnetic bubble traps a sea of charged particles, or plasma. A huge amount of this plasma is actually supplied by one of Jupiter's own moons, the volcanically hyperactive Io, which constantly spews sulfur and other materials into space. Now, as Jupiter spins, its magnetic field acts like a cosmic paddle, grabbing this plasma and forcing it to rotate along with the planet. The Galilean moons, however, orbit at their own speeds within this rotating sea of plasma. This difference in speed is the key. When a moon moves through the plasma at a different velocity, it creates a disturbance, like a rock in a fast-moving stream. This disturbance generates incredibly powerful electrical currents that flow along Jupiter's magnetic field lines, creating a direct electrical connection between the moon and Jupiter's upper atmosphere. Think of them as cosmic power lines, channeling immense energy from the moons straight down to the planet's poles. When the electrons carrying these currents smash into the gases in Jupiter's atmosphere, they excite the atoms and molecules, causing them to glow. And that glow, seen from our telescopes, is the auroral footprint. The energy doesn't travel instantly, though. The messengers that carry the signal of the moon's disturbance are a special kind of electromagnetic wave called Alphine waves. When a moon plows through the plasma, it generates these waves, which then surf along the magnetic field lines down to Jupiter. The time it takes for these waves to make the journey depends on things like the plasma's density. This travel time means the auroral footprint doesn't appear directly at the magnetic connection point of the moon. Instead, it appears slightly ahead, in the direction of the plasma's flow. This offset is called the lead angle, and it's a fantastically useful tool for scientists. By measuring this angle, they can probe the conditions of the magnetosphere near the moons, deducing information about the plasma density and temperature without ever having to send a probe right there. Now let's meet the cast of characters, because each of the 4 Galilean moons creates a unique footprint, reflecting its own distinct personality. First up is Io, the volcanic dynamo. Io is the most volcanically active body in the entire solar system, constantly erupting and feeding a dense, donut-shaped cloud of plasma called the Io plasmatorus that encircles Jupiter. As Io orbits within its own plasma cloud, the interaction is incredibly intense. This generates the brightest and most well-studied of all the footprints. For a long time, we thought it was just a single bright spot. But recent, stunningly high-resolution images from NASA's Juno spacecraft have shown it's far more complex. The footprint can appear as a mesmerizing swirling pattern, sometimes looking like a von Karman vortex street. That's the repeating pattern of swirling vortices you see when wind flows past a tall building. This structure tells us the interaction between Io and Jupiter's plasma is incredibly turbulent and dynamic. Io's footprint also has a long trailing tail of light that can stretch for hundreds of kilometers. This tail is thought to be created by the Alphen waves literally bouncing back and forth between Jupiter's upper atmosphere and the Io plasma torus, creating a series of secondary spots that fade with distance. Next is Ganymede, the largest moon in our solar system and an absolute game changer. Ganymede is the only moon known to have its own intrinsic magnetic field. This creates a mini magnetosphere nestled inside Jupiter's larger one. This unique setup means the interaction isn't just between Jupiter's magnetosphere and the moon, but between two magnetospheres. This complex magnetic handshake results in a distinctive auroral footprint. Instead of a single spot, Ganymede's footprint is often split into two. Scientists are confident this splitting is a direct consequence of Ganymede's own magnetic field. By studying the shape and characteristics of these twin spots, we can remotely study the hidden structure of Ganymede's internal magnetosphere. It's like performing an MRI from millions of kilometers away. Future missions, like the European Space Agency's JUICE Explorer, will give us an even closer look at this fascinating moon-within-a-moon system. Then we have Europa, the enigmatic ocean world. A primary target in the search for extraterrestrial life, Europa has a global ocean of liquid water beneath its icy shell. Its auroral footprint is dimmer than Io's or Ganymede's, but it provides crucial clues about the moon's environment. The footprint's brightness isn't constant. It varies significantly. This variation seems to be linked to Europa's journey through Jupiter's plasma sheet, a tilted, dense disk of charged particles. When Europa's orbit takes it deep into this plasma sheet, its auroral footprint shines its brightest. By tracking these changes, scientists can learn about the density and even the composition of Europa's extremely tenuous oxygen atmosphere, which is vital for understanding its potential habitability. The constant bombardment of radiation shapes the chemistry on its surface, and the footprint is a direct monitor of that interaction. Finally, we have the elusive ghost, Callisto. As the most distant of the Galilean moons, its interaction with Jupiter's magnetosphere is much weaker. For years, its auroral footprint was a phantom. Scientists searched and searched with the Hubble Space Telescope, but its faint glow was always lost within Jupiter's main auroral oval, a much larger and more dynamic ring of light. The breakthrough finally came thanks to NASA's Juno spacecraft. In 2019, a strong solar wind event hit Jupiter, compressing its magnetosphere. This conveniently pushed the main auroral oval out of the way, revealing Callisto's faint signature for the first time. In an incredible stroke of luck, Juno's flight path took it directly through the magnetic field line, connecting Callisto to Jupiter at that exact moment. Its instruments were able to sample the particles and fields responsible for the footprint, confirming its existence once and for all. This discovery completed the family portrait of the Galilean auroral footprints. So why does all this matter? Studying these glowing spots is more than just appreciating a beautiful cosmic phenomenon. It's a powerful diagnostic tool for understanding the entire Jovian system. By tracking the precise locations of the footprints, scientists can map Jupiter's complex magnetic field with incredible accuracy. When the observed footprint location deviates from a theoretical model, it helps researchers refine their understanding of the planet's deep interior, where the magnetic field is generated. The dynamics of the footprints, like the swirling of Ios or the splitting of Ganymedes, reveal the intricate physics of how plasma behaves in extreme environments. In fact, Juno's close-up observations have already discovered new types of plasma waves in Jupiter's auroras that challenge existing theories. Furthermore, the footprints give us a unique window into the moons themselves. The brightness tells us about the composition of their tenuous atmospheres. For ocean worlds like Europa and Ganymede, understanding this magnetospheric interaction is crucial for assessing their habitability. The intricate dance of light at Jupiter's poles is a story written by its moons. It's a remote probe, a magnetic field mapper, and a window into worlds that may harbor life. With Juno still sending back data, and future missions like the Europa Clipper and JUICE on the horizon, this story is far from over. The auroral footprints of Jupiter will undoubtedly continue to unlock new secrets about the king of planets and its fascinating family of moons for many years to come. Thanks for listening to G Fun Facts Online.